Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I'm learning quickly, I don't claim any real expertise. Today, we're looking at the 66th Project Euler problem. As always, I will link to the problem and my repository in the description. Let's dive in. Problem 66 is the Diophantine equation. No, I don't know that I'm pronouncing that right. Consider quadratic Diophantine equations of the form x squared minus d times y squared equals 1. For example, when d equals 13, the minimal solution in x is 649 squared minus 13 times 182 squared, which is equal to 1. It can be assumed that there are no solutions in positive integers when d is square. By finding minimal solutions in x for d equals 2, 3, 5, 6, 7, we obtain the following. Hence, by considering minimal solutions in x for d less than or equal to 7, the largest x is obtained when d equals 5. Find the value of d less than or equal to 1000 in minimal solutions of x first the largest value of x is obtained. Okay, so some algebra going on here. Copying over our problem. Actually, let's do it this way again. It's 30,000. Okay. And then this equation is this, which I am going to rewrite as x squared minus 1 equals dy squared. Okay, and the reason that I'm going to do that is because we're going to be finding the d, and then we're going to be looking for the minimum solution of x. So, go grab our favorite date time lines. Okay, and then limit is equal to, I'm going to start with 7 to prove out the concept, and then we'll change it to 1000. Because what I want to be able to see is we are going to have d equals 5 and x equal to 9. Then I'm going to say for d in range, the smallest number this can be is 2. Because 1 is technically a square, I think. And then plus 1. And then we're going to have a max x, which is equal to, I'm going to start it at 0. And then for max x, I'm also going to set that to 0 to begin with, because it doesn't matter. And what is our little algorithm going to be. So first, make sure D isn't a square. Then go through X, starting with oh, what's a good starting? I'm gonna say 1. And then for each X, calculate Y. And if Y is a whole number, check X against max X and save if larger. Okay, and then at the very end, we're going to print and we're going to say found largest value of X to be X for D equals D max X. Okay. We're going to need to import math. I'm just going to make this a function. I don't think I need to, but I'm going to say is square. And I'm going to take in num. Just take an in. And then root is equal to math.square root of n. And then I'm going to just return root mod 1 is equal to 0. So if that is true, then it is a square. Otherwise, it's not. It is square D. I don't need these outer parentheses. What am I doing? Just continue. We'll ignore that. And then I'm going to say x equal to 1. And while true, actually I'm going to say x equal to 0. And then x plus equals 1. And then I'm going to calculate y, and I kind of started this here. Okay, so x squared minus 1 divided by d is y squared. So x2 is equal to x times x. Or let's just say y is equal to math dot square root x squared minus 1 divided by d. If y mod 1 is equal to 0, then we want to do... Actually, we just want to break at that point. For the first time we find a whole number y, we're just going to break. Actually, this is going to be minimal x found. And x is greater than max x, then max x equals x, and d for max x is equal to d. Okay, so again, we'll try it with the number 7 first, just to see. Found largest value of x to be 1 for d equals 2. Okay, let's try starting with x equals 1 and see if we find a different answer. Still wrong. I have a feeling I am supposed to be doing this somewhat differently. In other words, possibly I did my algebra wrong. X times x, subtract 1, divide by d. I'm just going to call this y2 is equal to all of this. And then I'm going to say if y2 divided by 1 is 0, mod 1 is 0, then we do the rest of this. Let's see if that gives us a different answer. No, it doesn't. Okay, well, that kind of makes sense that it wouldn't. Okay, so let's do this a bit differently. Or at least let's try to do this differently. So we find x squared. We find x squared. And then that is going to be 1 larger than d times y squared. Let's do a print here. X equal x and y equal y for equal 3, 2, 9, 5, and 8. Okay, hold up. So, b equals 2, 3, and 2. B equals 3, 2, and 1. B equals 5, 9, and 4. D equals 6, 5, and 2. D equals 7, 8, and 3. Found the largest value of x to be 8. I'm just gonna move this line down here real quick. In what world is 8 larger than 9? Okay, so comparing 3 to max 0. So obviously 3 should win. 5 to max 9, comparing 8 to max 9. Oh, I didn't use my max x variable. That's my whole problem. How about now? And that is the correct answer for a limit of 7. Now go to our limit of 1,000. And this should go through very, very quickly. A little bit, instead of wanting to use this is square function, I'm just going to inline this. Sometimes you don't need the functions. I thought it might be more complicated for some reason. That was really confusing. Probably somebody is watching this and going, why can't you see that you're using the wrong variable there? Okay, so this is taking a little bit longer, obviously, because this is sort of an n squared, in that each of these numbers, we're only going through 998 numbers, values for D, but for each value of D, we're going through effectively every number X until we get to the correct Y, which could be quite a while. There's probably a good way to speed this up, which is, I think that X always has to be... Nope. I'm going to eat my words immediately. I was going to say X always has to be larger than D, but in the case of D equals 3, it doesn't. So, who knows? Kind of just going to see how long this takes. Give it a couple of minutes. I think we've already passed our 1 minute time limit, but kind of want to see if I get the correct answer, regardless. The good thing here is that we're just doing some maths, so we know that, like, each loop, each iteration is very, very, very quick. The problem is we have possibly a gigantic number of iterations. For instance, we saw that for 13, the lowest, the maximal number is like 649. But I don't think we have a good way to minimize how long we go here. Especially since, like, X is obviously not always iterating. It's not always getting bigger. And there's not a super clear relationship between these numbers. Um, there is something we can do, I think. Well, maybe not, because I was trying to think, can we do some sort of, is x squared has to be evenly divisible by d, but that doesn't quite work. So let's see, 9 squared is 81, minus 1 is 80, and then 80 divided by 5. Okay. And I kind of feel like we're doing something there already. Because we're dividing by d, and then we're checking whether it's a whole number before we bother taking the square root. Okay, it's run for about 4 minutes already, which is obviously too long. There's got to be a better way of doing this. Let's see. Minimal solution. I feel like finding... Going through every single value of x is rarely the right way to go about problems like this. Maybe we should look for a y instead of an x, because the y is always smaller. Yeah. We'll just sort of flip. Go ahead and keyboard interrupt that. So y can be as small as 1, so I'm changing this to y equals 0. And for each y, calculate x using x squared is equal to 1 plus dy. X is equal to math dot square root of y times y times d plus 1. That has to go inside the parentheses there. And then if x is a whole number, minimal x found, because x always has to be larger than y. And the minimal y has to be related to the minimal x. And then here we just delete this. And we're just going to take this chunk of code right here and put it before this break. Let's make sure this still works for a limit of 7 real quick, since we know that happens almost instantly. I'm going to convert this to an int before doing that. 9 for d equals 5, correct answer. Up our limit to 1000. I don't know if this will be any faster, but it's got to be at least a little bit. But I think there's a better way still to find this. Let's just look up how to solve these types of equations. Okay, this isn't... Okay, so they've apparently changed what these equations are. Ah. Okay, so this is talking about these two different equations. Let me make this a little larger for y'all. This is basically the general quadratic Diophantine equation that we are looking at, but a is equal to 1, a is equal to 1, k is equal to 1, and c is the number word incrementing. Slightly more general second order equation is what it then talks about for the rest of the article. It gets very, very mathy. Okay, this is not quite what we want. This is a whole book. Okay, this is yet more maths. Okay, not quite what we want. That is a calculator. This is where we were before. And it's going on about primes and whatnot. Okay. So we know D, and we need a better way of finding x squared and y squared. So, thinking about this algebraically, we can isolate the x or the y pretty simply. I've done both. But how do we know where to start for the value of y or x in finding the minimal solutions? Is there a better way than this trial and error I was doing? Because that is pretty clearly the wrong solution. So I have a D, I am looking for the minimal x. Smallest value of x that creates this as that makes this a true equation. Doesn't matter what the value of y is, as long as it equates to an integer. Um, okay. X squared minus 1 is equal to D times y squared. Okay, so if we have D, Let's think about it for d is equal to 2. We have x squared minus 2y squared is equal to 1. So we know that y has to be some number such that squaring it is still a lot less than x. So I feel like going at it by looking for the y first does improve our speed some, but obviously not enough. It's been running like almost 10 minutes now. So there's got to be a better way of choosing where to look for x. Is x ever larger than d cubed? So 13 times 13, I think, is not a very large number, 169. But then times 13, again, 2197. This is 649. So I think that x has to be smaller than d cubed. Though I don't really have any basis for that, other than in the few examples that I'm seeing here, it is not. I have a feeling we're getting stuck in an infinite loop somewhere. So I'm just kind of trying it again now. Let's see. Going back to the problem. I don't think there's any real relationship here, and I'm not sure how to optimize for this x and y value. Let's see. So y has to be less than x. Kind of significantly less, if you think about it. Although, obviously not for smaller numbers. X has to be somewhere. Actually, I'm gonna keyboard interrupt this again and just say y less than d. Because I think that y has to be smaller than d. Interesting. It doesn't have to be smaller than d, that just artificially limits it. Because y is larger than d is for number 13. Let's try it that way. That doesn't work either. Never mind. Okay, so we need an x. We need a better way to calculate x or y. So x squared is going to be times y times d. So is there a way to say if this isn't going to be a square root? So for b equal to 13 and y equal to 100. 100 times 100 is 10,000 times 13 would be 130,000. So 130,001. That's not going to be an even square. I honestly thought this double looping thing was going to work a lot faster than it did. Okay, so this is... Let's go ahead and graph x squared minus 13y squared equal to 1. Assuming that there is an online graphing calculator. Okay, so x squared minus 13y squared equals 1. Did I do that correct? It doesn't seem like I did that correct because this graph does not meet. X equals the square root. So, real quick. We know that x, smallest whole value of x is 649. So we kind of look at this graph. There, 649. But how do we get there from 13? Especially programmatically, how do we know to get there? Implementing by 1 isn't fast enough, obviously. Graphing it like this makes things a bit easy, but how do we know that? That's something we can do with. So like x equals 640 or y equals 175. That's really close to 631, honestly. Actually, it's kind of indistinguishable. Yep, we gotta scroll in real far to see that. Okay, so what I want to know is what is a good way to guess this? Like, not knowing. Let's see. When x is equal to 1, then y has to equal 0. When x is equal to 2, hmm, okay, this is that calculator we found previously. Okay, tiny print. Okay. Least positive primitive solutions. So, x squared minus dy squared equals n, where d is greater than 0 and not a perfect square. This finds least positive primitive solutions for the Diophantine equation, x squared minus dy squared equals n for d greater than 0, d not a perfect square, and each equivalence class of solutions. Then all positive solutions in a class are obtained by multiplying each least solution by, I don't remember what that Greek letter is called, to the n greater than or equal to 0, where that is the least solution of Pell's equation. Okay, so Pell's equation is actually the one that we're working with. Let's go Google this. We are interested in solutions where x and y are integers. The same solution will always mean that kind of solution. The obvious solutions where one of them is 0 is trivial. Okay, and then it goes on as to why it can't be a perfect square. And this is elementary method is what I was doing by finding one where dy squared plus 1 is a perfect square. And then Lagrange has this theorem tabulating dy squared plus 1 until it takes a square value. You're guaranteed the search will eventually terminate, but we are not assured how long it will take. In fact, the smallest positive solution can be unusually large compared to the size of d. Okay, so obviously looking at 61 and 109, it's very, very large numbers that we're dealing with here. Okay. Okay, so triangular square numbers. Okay. Just gonna scroll past this for a second. Okay, triangular square numbers correspond to solutions of this, but only for -2. For only d equals 2. goes deeper. Okay. X plus y square root of d. Okay, this is not making very much sense to me. I think this is helping. Square root of d. One of the conversions of the square root of d, one of the rational approximations of the irrational number d, found by truncating the continued fraction expression, is a solution to the equation. From this solution, all other solutions can be found. The way in which these solutions are generated shows that there are indeed infinity of them. Let's check out this Wikipedia article. Okay. Something. So it's always of kind of this form. Divided by y is an approximation. Square root of 2. Okay, so this is actually related to this convergent fraction thing. Okay. And there's other methods. I think... Let's go ahead and look for the square root of 13. Actually, perhaps a more interesting case. So, we've actually looked at problems that use these continued fractions before. This might be the best one to look at. Okay. So, Let's just look at the square root of 5 for a second. So when d is 5, we want to get 9 and 4. So the square root of 5 is 2 point something. And if we use this 1 over approximation, the square root of 5 is equal to 2 plus 1 over 4 plus 1 over 4 plus 1 over 4. So even 4 plus 1 over, or sorry, 2 plus 1 over 4 would be 2 times 4, which is 8, plus 1, which is 9. So the minimal solution is the very first fraction approximation using this sort of continued fraction things. So now that we know that, we can quite easily attack this problem. So I'm going to pull out root because we will need root. And then we're going to look back at problem 64. I don't think we care about extra special precision for this because we only need the first two numbers. And that's going to be the root find, I'm going to call it it's not called the principal. Of period period 0 is equal to wrong problem. The integer version of this number, and then period 1 is what happens when we subtract the integer part and then divide 1 by that number. So period 1 equals the integer form of, or let's just do this. I'm just going to copy this over for a second. So period 1 is equal to int of 1 divided by root minus period 0. Okay, so all that does there is it gets us this kind of integer. They're frequently quite small. And then it's 1 over period 1. So x is equal to period 0 times period 1. And then y is literally just plus 1. Gotta add the 1 on there. Y is equal to period 1. And I feel like I should double check that this is correct somehow, but I have a feeling that is unnecessary. Okay, so now we just have a much more efficient way of doing this. This is going to be O of n instead of like O of n squared or whatever. Not really O of n squared the way we're doing it before, but like... Okay, so that ran practically instantly, and D is 962. Find the value of D. So I think that's the correct answer? Okay, nope. Let's check 1923. Okay, let's double check our equation. Let's say if D is less than 14, we are going to print found x equal to x and y equal to y for d equal to d. Just print the first few. Okay, so x equal to 4 and y equal to 1 is obviously incorrect. Let's see where we went right. So the first one we got right. The second one, 2, 1, 3. 5 is 9 and 4. 5 and 2 for 6. And then for d equals 7, we ended up with 1 and 3 instead of 2 and 5, which is what it should have been. And then for 8, we don't actually know what it is. Okay. So, important lesson learned here, which is it's not enough to just go find the first couple numbers of the period. We have to go deeper than that. Yeah, x equals 4 means that x squared would be 16. And 16 minus 1 is 15, which if we divide it by 13, it's not going to be 1 squared. Okay, x squared minus 1 has to also be... has to also be a power of d. Or not a power of d, but d times something. I think. X squared minus 1. So, like, for 5, there's 5 and then 10. 5, 10, 15. 9 squared is 81. Minus 1 is 80. So, another way of doing this more programmatically would be to for every multiple of d, find a square. But how many times does d go into 649 squared times 1? Or plus 1 minus 1? Okay, 32,400. Still quite a lot. Still quite a lot. So, what's a good way of finding the next number for the periods here? Okay, so d, let's see. I'm just gonna not like that. X is equal to, and let's convert y squared into some other variable right now. So x equals square root, let's say x squared is equal to 1 minus the y squared, which means that if we have d, it has to be multiplied by a square. Or no. Actually, yes. D has to be multiplied by a square. Should be a plus symbol. D multiplied by a square plus 1 is x squared, so it's really... I'm reinventing what I had before, aren't I? Where I just go through y's. Let's see. Problem 64 goes through n less than or equal to 10,000. Going back to problem 64, this is like the square root of n. Okay. So if we go back to this problem 64, and we use it to find the periods for these various d's, then we can use it to find the minimum value for x and y. So let's go ahead and import decimal and have this precision here. at. Okay, so we don't need this check because we've already done this check. Now we want to keep the a of 0. Okay, and we know this works at least for up to 10,000. Because otherwise I wouldn't have been able to solve this problem. So now we have this period thing. And we want to be able to find these continued fractions based on this period. Let's see. Actually, A0 we probably don't want inside of the period. We want it separate. So, we're going to do something dangerous, which is build another while true loop here. While true, wait, what is this thing called? Okay, doggos, please stop. Convergent. Convergent fraction. And y as denominator. If equation works. If equation works, break. And then we'll do that part. So in other words, we're going to say yeah, I'm not sure how we can go through this. Like, we have 3 over 2. How do we just do, like, 2 plus 1/2? Okay. But then it's not 5 plus 1/2. And 2 plus 1/2 is going to be 5/2, not 7/5. I know how to work through it backwards, but that may not be good enough. Let's see, go back to this example. So for square root of 2, there was this pretty clear pattern. Where each denominator, each new denominator was the previous two terms added together, and each new numerator was the new denominator plus the previous denominator. So 5 is 2 plus 3, 7 is 5 and 2, 12 is 7 and 5, 17 is 12 and 5. I don't think it's that simple for most of these numbers. Like, for instance, E in particular doesn't act like that. And then if we can create these fractions, you're gonna just have to excuse my hard typing, hard drawing. So, let's see. Not quite what I want. That's the one I'm looking for. No. Or is it? Okay. So, square root of 3, just for instance, is 1 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 2, etc., and so forth. It just kind of keeps going down. So if we want to calculate for the square root of 3 these convergent fractions, the first one is 1 plus 1 over 1, so 2. And then the second one is 1 plus 1 over 1 plus 1 over 2, so 1 plus 1/2 is 3/2. 1 divided by 3/2 is 2/3. 1 plus 2/3 is 5/3. And then going to the next one, which, am I even doing that right for the square root of 3, 5 and 3? Well, here's I've gone too far for the trivial case of the square root of 3. Because it becomes 2 over... This is actually 2 over 1, and that first convergent fraction is, in fact, the correct answer. Let's just keep going a little bit. Or actually, let's change up to square root of 5, which is a little bit easier because it's 2 and then 4. What about the square root of 7? That might be a little bit more challenging. So, well, let's just draw out square root of 5. This is square root of 5 equals 2 plus 1 over 4 plus 1 over 4. And we can see here, because 2 plus 1/4 is 9/4. That's our correct answer again. Square root of 6, I believe, also is the trivial case, where it's 2 plus 1 over 2. So 5/2. And 7 the trivial case, so 7 is 3 plus 1 over 1. Or sorry, 7 is 2 plus 1 over 1, which is 3. Okay, so not the trivial case for number 7. So number 7 is equal to 2 plus 1 over 1, 1 over 1, plus 1 over 1, plus 1 over 4, and then it continues from there. So this is 2 plus 1 over 1 is 3 over 1. And then we continue. 1 plus 1 over 1 is 2. 2 plus 1 over 2. 2 plus 1 over 2 is 5 over 2. And then 1 plus 1 over 1, again, is 1 plus 1 over 1 is 2. 1 over 2. 2 plus 1 over 2 is 5 over 2. Flip it over to 2/5. And add 2. So wait, seriously? 9 over 2? That doesn't seem right. I'm going to double check my math. 1 over 1 plus 1 is 2. 1 over 2 is 1 over 2. Plus 1 is 3 over 2. 2 over 3 plus 2. I didn't do this correct. It's actually 8 and 3. Okay, so maybe starting to see this pattern. Are these all Fibonacci sequences? Sort of. Okay, so 2, and then 1 over 1, then add in a 1 over 2. See, when we add the 1/4, it becomes 5/4. which becomes 4/5, or when we add the 1, that's going to be 9/5, which is then immediately 5/9. Adding the 1 is 14/9. Flipping it, 9/14. 14 times 2 is 28. 28 plus 9 is 28 plus 9. Come on, brain. 37/14. So it's when we get these numbers that are not 1s or 2s that the pattern becomes confusing. Oh, maybe this is the pattern though. So 37 is 8 times 4 plus 5. And 14 is 3 times 4 plus 2. So I think that's how this is going to end up working. Is each number, each new convergent fraction is multiplied by whatever the next number in this period sequence is, and then added to the fraction that's previous. So let's test this out with E real quick, just to find out. So in this case, 2 is 2. It just starts with the number 2. The first fraction version, 1/1 plus 2 is 3/1. So, in other words, that one we have to kind of calculate manually, don't we? And then 2 times 3 plus 2 is 6 plus 2, which is 8. And then 2 times 1 plus 1 is 3. And then 11 is 8 times 1 plus 3. 3 times 1 plus 1 is 4. 19 is going to be 11 times 1 plus 8. 7 is 4 times 1 plus 3. Okay, so now we've figured out how to do this better. And the formula is each numerator is actually, I wonder if that works for square root of 2, since these are all 2s. 2 times 2 is 4, plus 1 is 5. 3 times 2 is 6, plus 1 is 7. 7 times 2 is 14, plus 3 is 17. 17 times 2 plus 7 is 34 plus 7, which I think is 41. Yeah, that's 41. And then 29 is 12 times 2, which is 24, plus 5 is 29. Okay. I think that's the general pattern. So in other words, x of n over y of n is equal to, and I'm just going to do this, x of n minus 1 plus, I'm going to say p times x of n minus 1 plus x of n minus 2. That's not readable, but don't worry about it. And then it's p times y of n minus 1 plus y of n minus 2. I'm not going to bother writing it all out. Okay, so now, if we find these periods, which we should be able to be doing pretty quickly, the first num is just a0. And the first denominator is 1. And then we know that that can't quite be the case. So we have to calculate basically the second one. So the first fraction version is always going to be a of 0 times that very first number. And then the denominator plus 1. I almost forgot. Plus 1. And then the denominator is just gonna put x equals 0. The denominator is period 0, and that's the first one. So while I basically want while not satisfies. Let's make this. XY. X is the numerator, Y is the denominator. Oh, I also need to take in the D. Giggity. Let's actually call this x of n. That's x. Sorry, that's y of n. X of n1 is a 0 at first, and y of n minus 1 is 1 at first. So x of n and y of n. Okay, so the first y equals y of n, and then the second, first x equals x of n. Because secretly this is going to end up being n minus 1 and n minus 2. It's fine. So here, basically, we're going to say if actually return x times x minus d times y equals 1. Looks simple enough. Will it work? Let's find out. So now x is going to end up being actually index plus equals to 1 if index equals the length of period, index equals 0. This should be a double equal sign. That's my bad. Now, x is going to be feel like having this is... I don't think I need these secondary variables here. I think I can just do this. X in 1 going to equal x. Y in 1 is going to equal y. I have to flip these because I did this wrong. And then x becomes what's the little equation I came up with? Oh, right, that's why I had that. Xn minus 2 equals 0. Xn minus 2 equals 0. Y. X of n2 is equal to x of n1. Y of n2 becomes y of n1. This isn't going to work the way I want it to work. Where is it? No, this will be fine, I think. Then x of n1 equals x. And y of n1 is y. Basically what I'm doing here is I'm just sort of scooching the numbers back, and now I know that y is equal to, or x is equal to x and 1 times period at index plus x and 2. Same thing for y. Okay, so using quite a few variables there that maybe I don't need to use. Let's bump this back down to 7 and see if I'm getting the correct answer. Actually, I guess I don't need to do that. So, still definitely taking quite some time, but I'm getting the correct answer for 13. So, maybe I'm getting the correct answer altogether. And it went from 1840 to 1841, so 1 second. Much, much improvement. Let's find out if I'm right. And that is the correct answer. Okay. So, this one really, really builds on some of the earlier Project Euler problems where you have to know about these convergent fractions, you have to know about the continued fraction periods that help to create the conversion fractions, and you have to figure out this formula, which I probably would have benefited from in the last problem. But yeah, we found the correct answer. We did it in about a second. I'm going to go ahead and delete that print statement. That just does the little check for us. I mean, honestly, we don't need to be keeping y because we could be checking whether y is a whole number, and that would probably speed us up slightly. So let's go ahead and make that refactor real quick. And then here y is equal to... You can bring math back. Math dot square root of x times x minus 1 all over d. And then return other y mod 1 is equal to 0. Could also do y is equal to integer y. And we should still get the correct answer. Oops. I did not fully take out all of these unnecessary pieces. Okay, so now we're finding the wrong answer. So I'm probably not checking for y properly. So I'm going to go ahead and undo that refactor so that I have working code. There. That's checking myself. 661. Okay, so I'm going to call it there for today, and I'll catch you in the next one.